Hi students, today we are going to see an important topic in data structure called AVL tree. So AVL tree came into exist because of the shortage or disadvantages of a binary search tree. So first we will see what is binary search tree followed by AVL tree. So binary search tree is a type of binary tree which has the condition of binary tree, but the only difference is that the left child should be less than value of a root node and the root node value should be smaller than the right subtree value. So nothing but the root left right is there. In that root node the left cell should be less than value of root and right should be always the greater value of the root, and each node should have only at most 2 children. So this is the condition for binary search tree. So we have seen already about this in before video. So characteristics that each node should have at most 2 children. The left should have the smaller value from the parent and right should be have the greater value greater than parent. So the important point to note here is it follows in order traversal. In order traversal is left child, root and right child. So this is the in order traversal for the binary search tree. So in this we will see an example here. So now we are going to see an example like 10, 20, 30, 40, 50. So now we are going to try to insert the element. We are going to form a binary search tree using these elements. So first, always the first node is considered as a root node. So here the first node is 10. So 10 is the root node. So next comes the 20. Now we are going to try to insert 20 in this binary search tree. So 20 is greater than of 10. So we have to insert in the right subtree of a root. So 20. Next is 30. So in 30, we have to check with the root node. The root node is smaller, so it goes to the right subtree. So now in right subtree we have only 20. So 30 we have to insert at the right sub. So next one is 40. So 40 is greater than 10, greater than 20, greater than 30. So we have to insert right of 40. Next one is 50. So 50 is also the same case like greater than 10, greater than 20, greater than 30, greater than 40. So we have to insert at 50. So in this case the binary search tree becomes skewed. So it becomes in one direction. So left child is, there is no left child. So the height of the tree is 5 because 1, 2, 3, 4. Sorry, 4. So in this process, this is the main disadvantage we are facing in binary search tree. So if numbers are like greater than or less than the root node, it becomes skewed. So to overcome this skewed disadvantage in binary search tree, we have developed we are going to study about the AVL tree. So we know first we have seen what do you mean by binary search tree. So after that we are seeing the disadvantage of binary search tree. So if you see here, the binary search tree becomes efficient, provides efficient searching, insertion, deletion. But if data is inserted in sorted order, then it becomes unbalanced. So when it is unsorted, there is no problem in binary search tree. But when the incoming elements is always already sorted, then the unbalanced or skewed process arrive in binary search tree. So to overcome this, we are going to see AVL tree. AVL tree. So AVL tree is a special type of binary search tree. We have seen enough of binary search tree in before the video. So next one is it is called a self-balancing binary tree. In that meaning of self-balancing is when we are going to try to insert a node in a tree, if the following condition gets violated, it will automatically balance the tree itself. So AVL tree is called as self-balancing binary tree. So it automatically maintains balance after insertion and deletion. So whenever we are going to insert an element, it will check whether the tree is completely balanced or not. So to check the balance, okay, next point is for every node, the height between the left and right subtree should always be -1, 0 and 1. We will see with an example this point. And the name why it came as AVL tree is because the AVL tree is developed by Georgi Andrel Velsicki and Evangeline Landis. So because of a name, it comes like AVL tree. So main we have to check in AVL tree is two things. One is balancing factor, and then that is height of the tree. So balancing factor is height of the left subtree minus height of the right subtree. So if the balancing factor is from -1, 0 and 1, then the tree is considered as a balanced one. If the value goes to 2 or -2, then there will happen a self-balancing one, which will be the AVL tree. So first we will see what you mean by height and balancing factor in the AVL tree. Now let's consider a tree. Consider this example in the binary search tree. So this is a binary search tree. So each node will have only at most 2 children, and the condition is that the left child should be less than value of root and the right subtree should be greater than root node, which is satisfy all the condition. So here now we have to, first point is height. The height is nothing but the number of edges formed. That is an easy explanation for we can easily find for 10 root node the height is 0. Sorry, the height is the number of edges formed in the tree. Therefore 10, the highest height is through the left subset. If you check 1, 2, highest one we have to check 3 and 4. So height of the left subshade is 4 and height of the right subshade is 1 and 2. So 4 minus 2 is equal to 2. So now the balancing factor is that left subshell minus right shell. So that answer is 2, but this answer 2 is not coming under 0, 1, 1 and minus 1. So balancing factor should always be from -1, 0 and 1. Here the balancing factor is of a root node is 2. So here the AVL tree condition failed. So we have to perform some kind of rotation here. We will be seeing in this class. So first this example is to see only the height and balancing factor of a tree. So for 4 the height is 0. For 3 the height is 1. The balancing factor of 3 is left child has no, so 0 minus 1 minus 1. So it gets evaluated. So here if you see for 2, the left child is 0. So 0 minus right child or height 1 and 2. So 2. So here the balancing factor is -2. So here also the property does not satisfy. So the advantage of AVL tree is it doesn't develop a tree and perform a balancing like this. Before insertion, after insertion itself, it will balance its all the nodes such that it follows the condition like balancing factor is 0, 1, 0, 0, -1 and 1. So now we will see the basic rotations performed in AVL tree. So after seeing an example, you can understand, like now you will see the definition. For every node, the height difference between the left and right should be at most 1. That means -1, 0 and 1. So balancing factor definition is height of left subtree minus height of right subtree. So that is the main condition for AVL tree. And next slide. is our type of rotation. So in AVL tree we have basic 4 types of rotation, that is called as left rotation, RR rotation means right rotation, left rotation, and right left rotation. So in this is the basic types of rotation. So we will see first an example. After that we will come and see the rotation, so that we will having a clear cut understanding of your AVL tree. So first, so here first one is left rotation. So left rotation means for example A, B and C. If you see this example, the balancing factor of A is 2 minus 0, that is 2. So the balancing factor should always be minus 1, 0 and 1. So here the balancing factor does not satisfy. So for this is L, this is L. So meaning of LL rotation is this one, L rotation. So in this we need to perform a right rotation. That means we are going to make a right B, we are going to make a B right. So B comes the center, C and A. So this becomes the right rotation. So first one, the left rotation. If you are going to see like this LL formation, you are going to perform a right rotation. So right side நம்ம B move பண்ண போறோம். So B comes first. So that is we are going to rotate B. So B and C come. For this is a left rotation. So example like 10, 5 and 2. So 5 is less than 10 and 2 is less than 5. So this is satisfied by balancing factor is 2. Now we are going to make a right rotation at element 5. So 5 comes at the center. So left side will be same. So 10 is always greater than 5. So it will come under here. So this is the first one, left rotation. So next we will see about right rotation. Next RR rotation, the same as LL rotation. So that comes at left side, this comes at the right side, like A, B and C. So here also the balancing factor is 2, but the direction is right. So right means first we are going to pop this one, we are going to move at the left side. So now B comes at the center, A comes the left child and C comes the right child of the B. This is called as right rotation. So in right rotation you are going to make a left turn. So left rotate. Kindly don't confuse between these terms. Example 10, 20, 30. So this is not balanced one. So we are going to perform left rotation at the 20. So 20 becomes the root node, 10 becomes the left and 30 becomes the right subtree. So this is an example for RR rotation. Next one is left-right rotation. By name itself you know, first the element is root node. So first one is left, B. After that it is going to be right. Sorry, here it is C. Left. So first it is in left side, next it is in right side. So it is called as left-right rotation. So in this we are going to perform two set of rotation. So in LL and RR rotation there will be only one rotate operation. But here we need to perform two type of rotation here. So first thing we are going to do here is left rotation. So left will be happening at C. So A, C, then B. Now also it doesn't satisfy the balancing factor. Now we are going to perform right rotation at C. So C comes center, B comes left and A comes right. So this is left right rotation. Kindly don't get confused. First one is we have to find what is LL, LR, RR or RL. So for that you have to check the direction of the balancing factor. So here the balancing factor is 2 because height of the left minus the right side equal to 2. In this case the left right, first we are going to perform left rotation at C. After making this, the resultant is this tree. So this is also not balanced one. So after that we are going to perform right rotation at C. So C comes at the center. Now check the balancing factor. So it doesn't have both A and B doesn't have no children. So balancing factor is 0. But the C has a balancing factor of 1. My height of the left side tree is 1. Height of the right subtree is 1. So 0. Now it is balanced one. This is left right rotation. So next we are going to see right left rotation. Now next one is right left rotation, RL rotation. So in this A, B and C. So this one is right side. After that C is in left side. So for we are going to see the balancing factor of A. It is minus 2 because left side height of the left subchild is 0, minus of right subchild is that is 2. So 0 minus 2 is balancing factor minus 2. That is not a condition for a balancing factor. So now we are going to perform rotation. So first we are going to perform right rotation at the C. Right direction la nama move panna porom. So A, C, A, C and B. Why we are telling is we are going to perform right rotation in C. Right direction la the C going to move. So here right rotation. After this, now also the balancing factor is minus 2. So after this we are going to perform the left rotation of C. C, A and B. In simple term we can tell this as the C will go to root node, C comes the root node, A comes left side and B comes the right side. So first we are performing right rotation, after that we are performing left rotation. So these are the concept of LL, LR, RL and RL. Now we will go with definitions of rotations. Now we will see the definition. So LL rotation means it will perform right rotation. So right direction it will move the element. So insertion occurred in the left subtree of the left child. Now first example we have seen LL direction. So that is the first one. RR means we will be right rotation. If it is formed, we will be perform left rotation. So the first two one will be in like opposite cases. Left rotation means right rotation will perform. Right rotation means the left rotation will be performed. So last two it will follow the same as the name. LR rotation means in the tree we will mark it as LR. Insertion occurs in the right subtree of the left child. So if you see with an example, you will be having a clear understanding of this AVL tree. So basic condition, basic rotations are LL, RR, RL, and RL. So in first LL and RR, that will perform only one rotation in the tree. But in case of LR and RL, we will be performing two rotations. So first we will make one rotation. After that we will be following another rotation after that. Only then the balancing factor we can attain. So now we know what do you mean by binary tree, what do you mean by binary search tree, and now we have seen the conditions of AVL tree. So to know the AVL tree, we need to understand two concepts. First one is height of a tree and the balancing factor. So balancing factor formula is left subtree, height of the left subtree minus height of the right subtree. So if the balancing factor is like 0, 1 and minus 1, then no problem in the binary search tree, we can leave it as such. But if the tree becomes minus 2 or 2, there will be a self-balancing method. So that balancing method is called as rotation. So here we have 4 rotation: LL, RR, LR and RL. In LL and RR we will be performing only one rotation, but in LR and RL we will be performing 2 rotation. We will see that with an example. So now we will go with an example for AVL rotation. So we will take an advantage. We have seen a problem, skewed problem, 10, 20, 30, 40, 50. So in the binary search tree, this have a disadvantage. That's why we came for AVL tree. So we will try to solve that problem. So first one is considered as a root node. So after considering that, we are going to insert 20, that is greater than 10. So it's going to be right side. So next one is now we have to, for each time we have to check the balancing factor. Balancing factor is 0. Here it is 1. It doesn't violate the condition. Next we are going to insert 30. In this 30, if we see here, after inserting 30, the balancing factor of 30 is 0. Balancing factor of 20, 0 minus 1, that is minus 1. Condition satisfied in both these two cases. In 10, the height of the left subtree is 0 and the height of the right subtree is 2. 1, 2. So answer is minus 2. So here what happens is the balancing factor doesn't satisfy. So we need to perform a rotation. So here we have to check the direction of the rotation. So this is in right direction and here it is also in right direction. So we are going to perform here the RR rotation. RR rotation means we are going to perform a left rotate at 20. So 20 becomes the root node, 10 becomes left child and 30 becomes right child. So now if you see, the tree is balanced. So here the balancing factor is 0. Here 1 minus 1, that is 0. So now it is, so hence because it is balancing at every insertion, it is called as self-balancing binary tree. So next we have to insert 40. So insertion at 40 is here. So if you are going to insert 40, now we need to check the balancing factor. So first we do balancing factor. So for 40, balancing factor is 0. For 30, height of the left is 0. Height of the left is 0 minus 1, that is minus 1, that is also condition satisfied. Here there is 0. So now we have to check the root node balancing factor. So height of the left subtree is 1, height of the right subtree is 2. Answer is minus 1. So this condition also gets satisfied. So now we are going to try to insert 50. So after inserting 50, we have to check the balancing factor. So to start with, balancing factor of 50 is 0. And for 40, 0 minus 1 is minus 1. For this one, you see, for 30 plus 40, for 30, here balancing factor is 0 minus 2, that is balancing factor is minus 2. So the tree here at this time the rotation needs to be performed. The direction is same, RR rotation. So we will be performing a rotation at the left of 40. So answer will be 10, 20, 10, 40. So in 30 comes the child of 40 and 50 becomes the right child of 40. Now the tree is balanced one. So here the balancing factor of a leaf node is 0. Here also 0 because 1 minus 1. So here 1 minus 2. So answer will be minus 1. So in such a way the binary search tree limitations is overcome by AVL tree. So next we will see another example which will be by including both the left-right rotation and right-left rotation. Now following the above example we are going to try to insert elements 7 and 8. So 7 is less than 20 and also is less than 10. So we need to insert the left of 7, that is 10. So next one we are going to insert 8. So 8 also is less than 20, less than 10 but greater than 7. So we are going to write that 8. So now we have to check the balancing factor. So 0, 0 for all leaf nodes. So here the answer is 1 minus 1, 0. So here balancing factor is 0 minus 1, that is minus 1, satisfied. So now we are going to check the balancing factor of 10. So for 10 height of the left child is 2 because here 1 and 2. So right is 0. So balancing factor is 2 which is not a balancing factor or condition for AVL tree. So here at 10 the balancing factor is not satisfied. Now we have to check the rotation. So here it is right side of root node, here it is left. So there is oral rotation. So in case of oral rotation, first we need to perform the right rotate at 8. So right rotate, after performing right rotation 20, so 10 and 8 and 7. So remaining we can put as such. So we have performed only one right rotation here. Still the balancing factor of 10 is not modified. So after this we are going to perform the right left rotation at here. So 20, 8, 7, 10, 40, 30 and 50. Now we will check the balancing factor of each element. So balancing factor of all leaf node will be 0. Here if you are going to check the balancing factor, 1 minus 1 is 0. Here also 1 minus 1 is 0. So here the height of the left child is for 20 is 2 and height of the right subtree height is 2. So it is 0. So now everything is very balanced to 1. Now the skewed or unbalanced binary tree is overcome by this AVL tree. So next we will see one more example. We will see one more example like 20, 30, 40 and here we are up to this the balancing factor is say once again 10. This will be a right example for our right left rotation. Now you check here balancing factor of 30 is affected, it is 2. So RL is performed here. So first we are going to the perform right rotation. 10, 30, 35 goes up, 35 and 40. So still balancing factor is not changed. So now we have to perform left rotation. 20, 10, 35, 30 and 40. So this is an example for first we are going to perform here left rotation right rotation followed by left rotation. So this is the concept of AVL tree. So we will have one more quick revision. First one is left rotation. In left rotation, so tree will be like this. So we are going to perform a right rotation at B. So we are performing right rotation. So B comes center, C and A. This is left rotation. Next one is right rotation. So if you see here, A, B and C. So it follows right path. So we are going to perform left rotation here. So don't confuse. So left rotation here. So B comes the center, A becomes the left child and C becomes the right child. Next one is LR rotation. Next one is LR rotation. A left side, then right side of. So if this follows, then we have to perform first right rotation, left right. So first we are performing left rotation, A, C and B. After that we will be performing the right rotation. So C comes the center, B left child and A right child. Next one, last one, RL rotation. So R of C. So first is right side, next one is left side. So here first we are going to perform right rotation here. So A, C and B. After that we are going to perform left rotation. So C, A and B. So now we have seen all the rotations covered in AVL tree. Left, RR, LR and RL rotation. Thank you.